Welcome to episode 21 of Travelling Science. G'day legends, welcome back to Travelling Science, the podcast that's sharing science with the world. My name's Jesse Crow and I'm the Travelling Scientist, coming to you today from my home in Aireys Inlet, Australia. I'm a health science communicator, and on this podcast we interview doctors, researchers and experts, hearing their stories and sharing their ideas that can help us to live smarter, happier and healthier lives. This week's guest is Dr. Aaron Dingle, a senior scientist and co-director of the Microsurgery and Regenerative Medicine Lab at the University of Wisconsin in Madison. Aaron got a PhD in vascular tissue engineering from the University of Melbourne, where I studied, and I actually attended his PhD presentation several years ago because Aaron is a good friend of mine. But I haven't really seen him since that day because he was essentially headhunted by the University of Wisconsin, and he's been over there ever since doing groundbreaking research in the areas of limb replacement, nerve repair, microsurgery, and neuroprosthetics. So I'm super excited to finally have him here on Travelling Science today to share with us his story and his wisdom. Throughout this episode, Dr. Dingle answers questions such as how we grow organs, what is microsurgery, can we create neural prostheses, which parts of the human body are hardest to reproduce, how science fiction can inspire scientific research, and why simple conversations can be life-changing. And we also discuss things like microvasculature, limb transplantation, stem cells, nerve repair and regeneration, pirates and prosthetics, Disney World, Star Wars, human tissues versus Kleenex tissues, and why you should drink more coffee. So let's get into it and learn all about the science of tissue engineering and limb transplantation with the one, the only, Dr. Aaron Dingle. Dr. Aaron Dingle, welcome to Travelling Science.
Thanks, Jesse. It's nice to be here.
No, it's awesome to have you here. Thank you so much for taking the time to come on the show. Would you like to tell us, what did you study at university?
So I studied biomedical science at Victoria University in St Albans. I did an honours there as well. And after that, I got a job as a research assistant for a couple of years, found out that I really enjoyed developing projects. And so transitioned from research assistant after 2 years to a PhD in vascular tissue engineering focused on the microvasculature of the liver.
So that's like creating artificial blood supply for a liver? Is that what that is?
So it was looking at creating an artificial liver, but effectively focusing on the microvasculature of the liver specifically.
Microvasculature means the tiny blood vessels, like the capillaries, venules, and arterioles, that are responsible for transporting blood to and from the organs and tissues around the body. So the microvasculature keeps everything healthy and functioning.
Liver has a really specific microvasculature called sinusoidal endothelial cells. They're different from typical endothelial cells, most notably because they have these large open pores in them that allow bigger molecules through. And so part of my thesis was that to be able to grow an efficient liver that was capable of doing all of the detoxification and production that livers do, that you would need these sinusoids in the endothelial cells. So the microvasculature is going to be really essential to the functionality of an end organ if you can grow that organ.
Absolutely. And the way you say that, grow a liver or grow an organ, like it's a normal thing, that's probably completely foreign to a lot of people. Where are we at with growing organs? How does one even grow an organ?
Well, I've been out of the tissue engineering field specifically for probably 8 years now. But the premise is that you can effectively take somebody's cells, whether it's a stem cell from fat or from bone marrow, or even take adult cells and revert them back to stem cells, which induce pluripotent stem cells. And then you can use different factors to differentiate those into specific cell types. So for a liver, then predominantly you're looking at a hepatocyte, which makes up at least 80% of the liver. And they're the cells that do all the detoxification and all of that sort of stuff. Then you can implant those as either immature cells because they have a higher potential to survive the implantation process, but you can also implant mature cells. And the key factor is that they need to get connected up to a blood vasculature to keep them alive, right? So if you have an immature cell that can deal with a little less oxygen than a mature cell, has a chance of surviving a little longer while it waits for a connection to the blood supply. And then I was trying to grow a pseudovasculature inside three-dimensional balls of hepatocyte precursor cells. So effectively, I was trying to have a mini vasculature in there already so that reconnection to the blood supply is faster through a process called inosculation, which is two vessels just joining up to creating one.
Wow. And so we would do that in the case of, say, someone having liver failure. We could take some of their stem cells and potentially create a new liver for them.
Potentially. The question you always get if you work in liver is, don't livers regenerate anyway? And the answer is yes. It's a very robust organ, and it is capable of quite a large amount of regeneration. And in fact, you can even do a partial liver transplant from a living donor. So you can take a lobe of my liver and, I could give that to my child if they needed a liver, and then my liver would replace itself, and the lobe that I would give my child would also grow into a full-size liver that accommodates an adult as they grow larger. I was focusing on inborn errors of metabolism. So sometimes you're just born missing a simple function, right? So if the liver has somewhere around 50 functions that it performs on a daily basis, right, and you're missing one critical factor, then there are part of the biological processes which don't work for you. And then you either need supplementation or potentially a transplant. And so this would be looking at growing livers that then could go, a small portion of a liver that then could be given to a child with an inborn error of metabolism that corrects that error, because you give them cells that have the necessary genes to make the products that they're lacking. And the estimation was, at least when I did my PhD, the estimation was you only need to replace about 10% of the total organ volume to be able to replace the missing proteins or functions. So you could just grow a small little piece of liver that would do that job, and then the rest of their liver would be able to function normally.
Very cool. I actually remember vaguely sitting in on your PhD presentation many moons ago, and I remember thinking that work was incredible. So that's awesome that you did that. And you said you haven't been there for quite a while now, 8 years or something. What have you been doing in the meantime? Or where are you at now? What are you working on currently?
I'm currently in Madison, which is in Wisconsin in the United States, in the Midwest, working at the University of Wisconsin, and I'm in the Department of Surgery, Division of Plastic Surgery, doing something completely different, really. So instead of growing organs now, I am looking at viable replacements that currently exist for large composite tissues, effectively. So my primary focus is limb replacement. Limbs contain multiple organs. So there's bone, there's muscle, there's nerves, there's blood vessels, there's skin. Each one of those has its own independent requirements. So they're considered composite allografts or composite transplants. Back when I did my PhD, there was some work looking at regrowing entire limbs from stem cells using decellularized matrix. I still have a bit of hope for that, but I don't think that's going to be realistic in my lifetime. So instead, I turned to something that I think would be more clinically applicable. And so I'm looking at neuroprosthetics, which are the capacity to control a robotic limb with your peripheral or central nervous system, and I'm focusing on the peripheral nervous system. And I'm also looking quite heavily at limb transplantation as well. So the concept that you can have a limb transplanted just as you would have a heart or a liver if you just so happen to lose one.
That sounds incredible. So a big part of that, I imagine, would be getting neurons connected up to prosthetic limbs. And that sounds super complicated. Is that something that we can do, or is that something we're working on?
Yeah. So neuroprosthetics is, I think, as viable as it's ever been currently. So about 8 or 9 years ago, there was a big push from the United States Defense Department, particularly DARPA, Defense Advanced Research Project Agency, to try and revolutionize prostheses. So the most common upper limb prostheses you'll see is a hook prosthesis. I think most people have probably seen one in their lifetime. They are not incredibly functional, but also they're pretty old technology. So they were invented following the Civil War as part of the Civil War manufacture, because with the invention of bullets and modern warfare, lots of soldiers were coming back missing limbs and they needed replacements for them.
I thought they were invented by pirates. No?
Not the hook prosthesis technically, but peg legs potentially, which is a lower limb prosthesis, right?
Right. Okay.
Simplistically, you could put like a bedpost with a connector to your leg.
There you go.
Hands are considered an incredible component of being human. It's one of the things that really evolutionarily separates us. And so you can imagine if you don't have one at all, or if you're missing one, life can be difficult. And I think one of the really valuable parts of moving to limb replacement as opposed to liver replacement is that I don't think people particularly think about their livers very often. To the same extent, I don't think people think about their arms or legs that often, but you use them every single day, and it's a little easier to get people to relate to the fact of, imagine if you were missing one, right? So take your dominant hand, put it behind your back, and use your non-dominant hand just for your morning routine and find out how annoying that is, and then imagine having to live that way.
So I tried this and it sucks. I mean, I'm sure you get used to it, but let me tell you, buttering toast with one hand, you might as well just go ahead and throw your breakfast on the floor because that's where it's going to end up anyway. So yes, I can definitely see the value in limb replacement.
And so being able to restore that function, I think, is integral to kind of allowing people to have high quality of life and do the things that they want to do. Because effectively, a major difference between losing a limb to having an organ that's impaired or failing, like a failing heart or liver, is that you won't die from missing a limb if you don't get a transplant. So you can be otherwise healthy and live a really long life. Right. And so it's important that that life is fulfilling and allows you to do the things that you want to do. In the same way that if you get a heart or a liver transplant, the whole point is to be able to keep you living and make sure that that life is enjoyable.
Look at you, saving limbs and saving lives. It's really interesting. It makes me think. I mean, there's this argument that a lot of modern science is derived from science fiction, in the sense that a lot of scientists see or read about these fantastic creations in films and books. And I've seen that you go on quite often about Star Wars, like on LinkedIn. And at the end of Empire Strikes Back, Luke Skywalker gets his arm cut off by Darth Vader and gets it replaced with this new biomechanical arm. And I wonder if that story has somehow influenced you to be doing something similar in our modern world.
So that is directly linked to how I got this job. So when I was a research assistant at the O'Brien Institute of Microsurgery, which was a world-renowned institute for fellows from microsurgical fellows to come from around the world and learn cutting-edge microsurgical techniques. One of those people was Dr. Sam Poor, who was a microsurgeon from Madison, Wisconsin. We got along really well. We worked on a lot of projects together. Then his time in Melbourne was up and he came back to Wisconsin. In that time, I transitioned into a PhD. We didn't really have much contact over the next few years, but about 6 or 7 years later, I remember getting up at 6 o'clock in the morning on a Saturday to work on my thesis while everyone was still asleep. And I put Empire Strikes Back on to keep me company while I was writing. At the same time, I noticed that Sam was online, so I sent him a message to say, "Hey, buddy, how you doing? It's been a while. What are you up to?" And he said, "Oh, I just finished watching Empire Strikes Back with my son. And you know that scene where Luke gets his hand cut off?" And literally happening on my television at the same time. And I said, "Yeah, I'm familiar with it. I'm watching it now." And he said, "I just got a grant with DARPA to look at how to create prostheses that are controlled by the nervous system. Would you like to work on that project? How's your PhD going?" And I said, "Well, I'm trying to finish it right now. I'd love to." So I applied for that job. A few hours later, when my wife came downstairs, she just looked at me and she said, "What have you done?"
Honey, we're moving to America.
First year anniversary is coming up and it's paper, and I got us 2 one-way tickets to the US. And I've been here since.
Wow. I was wondering how you ever actually ended up in Madison, Wisconsin. I didn't realize it's partly because you were just watching Star Wars while you were finishing your PhD, and partly because you knew an incredible scientist over there who was working on this amazing project, which in a way relates to Star Wars. Fantastic. I love that.
And I think, just to kind of further your point, growing up, my parents were always telling me, like, what are you going to do when you grow up if you just spend all your time watching Star Wars and all these other sci-fis? But as you pointed out, a lot of what you and I grew up with watching in movie theaters and on TV is genuinely becoming a reality now. right? Even a lot of the technology that were in comic books that our parents might have seen, so Dick Tracy, if anyone remembers him, had a watch with a video camera in it, which you can get now from numerous companies.
Dick Tracy was a fictional police detective from a comic strip created by Chester Gould back in the 1930s, and it's theorized that this could be where the idea for the smartwatch came from. Almost 80 years before the Apple Watch was invented, Dick Tracy was using his watch as a two-way radio and video transmitter. So was this the original inspiration for the smartwatches that we wear today? Well, probably not. But it just goes to show that comic strips, TV shows, and movies can lead to technological advances in the real world, just like Luke Skywalker's robotic hand in Star Wars.
Prostheses are becoming robotized. The hope is that you can soon control them with both motor and sensory functions that replace a lost limb. And then some other projects that I've worked on in the past were things like improving learning rates and capacity to learn through vagus nerve stimulation or trigeminal nerve stimulation. And if you think about movies like The Matrix, there's that famous scene where Neo's about to fight with Morpheus, and he just says, I know Kung Fu, and then he does it. And that's the same concept, right? That you can stimulate these nerves and activate parts of your brain that improve your focus, improve your attention, kind of in the same way that caffeine might. And then you can learn something like a new language on the plane to your next holiday.
This concept sounds insane, and I actually made a video all about targeted neuroplasticity training when Aaron told me about it years ago. So if you want to learn more about instant electric learning, I'll put a video to that link in the show notes just below. But where do all of these incredible technological ideas even come from?
So much of what so many incredible people in all different fields do nowadays is inspired from things like TV and movies. So you're right. Sometimes sitting down and taking a break and watching something like Star Wars or any sort of movie or TV show, it can be really inspiring and potentially life influencing.
Absolutely. And I think it's through some of those experiences that I've finally, later in life gotten a bigger appreciation for art, but also the collaboration between art and science. And I feel like growing up, those two things were sort of treated as very different. Art was something that was really abstract and difficult to reproduce, and science is all about reproducibility and mechanisms and being very, very specific. But the majority of how we pass on scientific knowledge is through writing and reading. But it's not until you see somebody else's vision of something, which you get, beautifully in a movie. You can even see how something might function in real time, like a prosthetic arm. And you can say, oh, that's really interesting. And then you can kind of backwards engineer that and say, well, how would I make that happen? What would I need to be able to do that? And why aren't we doing it? And then you go and hit the literature and find out what people have done and find out that, 50 years ago, there was the first robotic prosthesis, and it required a Batman-like utility belt that was just a series of really heavy batteries. And it was a pneumatic hand, so it could only open and close, but it had wires that went all the way to the belts, and the concepts were there. These things existed, and we're now in a time where microchip technology means that it can be a legitimate reality.
So I found a paper linked in the show notes called The Evolution of Functional Hand Replacement, from iron prostheses to hand transplantation. And it shares a record of the earliest known prosthetic hand, which was in the year 201 BC, over 2,200 years ago, in which Roman general Marcus Sergius received a right hand made of iron, which was simply tied to his arm. And I imagine it was heavy, slow, weak, and easily compromised. But over the centuries, technology has improved, and 50-odd years ago, Russian scientist Alexander Kobrinsky created the first electric prosthesis, which was described in the literature as heavy, slow, weak, and easily compromised. But it was a good attempt.
Bring it back to your work in 2023, so 50 years after that first pneumatic hand. Where are we currently at with this technology? Are we able to control, for example, a prosthetic hand with our nervous system, or where are we at with that?
The short answer is absolutely.
Awesome.
The long answer is less than perfect.
Right.
The consensus is generally that we have a great understanding and capacity to provide motor control. So that's all the kind of reaching and grasping jobs that your muscles would do. The remaining challenge is trying to integrate sensory information into that system as well, so that you have what's called a closed loop, right? So the classic laboratory experiments you see for that for people with these advanced prostheses is trying to pick up an egg without breaking it, or trying to pick up a plastic water bottle that doesn't have a lid on it without spilling the water out all over your robotic hand, right? Because you can imagine that effectively knowing how much force you're putting in tells you when to start and stop. So it's a difference between trying to carry all the shopping bags in one go or picking up a baby, right? You do not want to use the same amount of strength for either of those jobs. You have to tailor it to the task, and you can't do that without feeling. You can do a little bit of it, like with visual perception. You can kind of grasp how much pressure or how much force you're using, but you ultimately don't have fine control over that. And really, coming back to the hand being such a wonderful part of human evolution, it's the fine motor skills that really kind of sets it apart.
Yeah, wow. And I imagine trying to get all that wide and working correctly would involve getting into some serious neuroscience and trying to figure out more about the brain, which is such a complicated organ. So that's really challenging.
Yeah, so a lot of the work started off in brain-controlled interfaces initially. So it would be an implant in your sensory motor cortex that then relayed the information to the limb. There are a few issues with that. One of them being that there tends to be quite a long learning time because you have to invoke plasticity in the brain and rewire it. So there's quite a lot of learning. But if you go straight to the peripheral nerve and plug in directly there, there's a limited amount of information being sent from the brain down that nerve specifically.
Interesting. It's almost like if a machine stops working because one of the outer cords has gone missing, you could potentially if you can just replace that outer cord and make that connection come back, it could work, and you don't even have to go into the inner workings of that machine or the human brain.
Yeah, you don't have to reprogram the software. You just have to replace the missing mouse or keyboard.
Very cool. That sounds incredible. You said you work in plastic surgery to some extent. Do you do any surgery, or is this like the academic side, or are you just doing experiments? Like, what does a common day look like for you in your work?
So I'm a PhD scientist, not an MD. No plastic surgery training. While I've performed and participated in surgeries as part of experiments in the past, I try not to these days. Part of being in such a department is that I have a wealth of resources of people that are better trained at surgery, particularly microsurgery, to perform these tasks better and with greater outcomes than what it would take for me to perform them, right? I mean, they've had years more experience.
When you say microsurgery, are we talking about working on like very, very small things like nerves, blood vessels?
Nerves and blood vessels that are fractions of a millimeter in size.
Yeah, right.
And then there are even super microsurgery, which is, fractions of millimeters.
I don't even want to get into how you would do that kind of surgery.
That's why I don't do it, and why I get people that have trained or are in training to become fully fledged microsurgeons.
Yeah, I'll do the research, you do the microsurgery.
Watching microsurgeons in action, you really get a grasp for how important their craft is, particularly in research. And I think from an outcomes perspective, that the kind of science I want to do and am doing is best served by people with expertise in microsurgery. And I think ultimately it means that I get better outcomes for all of the procedures that I do. So it's a higher standard of quality for the results. And I don't have to question whether there was, some kind of surgical error because I'd had too much coffee that day or some such. And you asked me about a typical day. A typical day for me is probably trying to cut my emails down to a manageable size for about an hour in the morning, visiting the lab and seeing who's running what experiments and if there's anything needed, how I can assist there. Often a few topics on procedures and methodology, as well as the opportunity to just kind of brainstorm ideas moving forward. I spend a considerable amount of time reviewing manuscripts that either my students are writing or for journals or writing grants or reviewing grants. And then the rest of the time is spent in various faculty meetings or lab meetings discussing processes and data acquisition and results and how to continue moving things forward. A lot of troubleshooting as well.
Sounds like a lot of fun. No, it sounds like a lot of intense thought work. You must be exhausted.
It's definitely neck-top computer heavy.
Yeah, but doing good things. Do you have any daily rituals to get you through all of that sort of work?
Oh, I mean, I live on espresso.
Yeah.
I have a machine on my desk and probably at least 1 an hour for the first few hours.
Oh, that's incredible. I believe that is very good for warding off neurodegenerative diseases in the future. So good on you.
Thanks, man.
To an extent, I think maybe there's a point when you get to too much. I'm not sure.
No, I mean, I've tried to find it. Certainly through my PhD, there are a few occasions where, you can almost see sound and you have to go home. And I think of all the things I've read in the dietary literature, coffee is the only one that I'm convinced has actual benefit. For all of the positive effects, things like increased attention span, increased focus, energy production, but there's also things like longevity, potential decrease in neurocognitive diseases, things like that. I think the second one to coffee is probably chocolate, but I feel like chocolate is in that stage where it has 50% of the evidence says it's the greatest thing in the world, and the other 50% says it's going to kill you. So coffee doesn't seem to have that also contradictory literature. Right?
Yeah, I mean, I'm a big proponent for tea myself. I drink a lot of black tea, green tea, and I feel like that has some positive capabilities. But with chocolate, I think it's the darker the better in general. Darker usually means less sugar and more antioxidants. And I recently did an episode on antioxidants, and they're pretty good.
Right. Kudos to antioxidants. They're important.
I have several videos on my YouTube channel, The Traveling Scientist, about all of these topics. So if you want to learn more about the long-term health benefits of coffee, chocolate, tea, or antioxidants, check out those links in the show notes just below. But for now, let's learn more about Dr. Dingle.
What do you do when you're not in the lab? What do you do when you're not doing all this meetings and email cutting down and serious thought work?
Then it's all family time. After that, 2 small children, 4 and 7, a 3-year-old dog, and a wonderfully supportive wife. And so the times there are just doing things together, board games, video games, adventures.
You watching the new Star Wars?
Yeah, all the Star Wars. I mean, this year we finally got to go to the Star Wars exhibit at Disney.
Oh my God, how was that?
It was phenomenal.
Was that in LA?
No, that Orlando. So Disney World.
Oh, I haven't been there, but I've been to the one in LA and it was mind-blowing. Very cool.
Yeah, I mean, it's they've done a great job of making it immersive. You just enter there and you feel like you're there.
What do you hope to achieve long-term through your work?
Ultimately, what I would like to see is at least one of my ideas translate clinically to be able to improve the lives of people, whether that is in enhancing peripheral nerve repair and regeneration so that people can have a return of function after they've had an injury, or whether that's something more significant like replacing a whole limb through neuroprostheses or limb transplantation. To that end, I think a lot of the limb transplantation work that I'm doing has huge opportunities in solid organ transplantation as well, so livers, hearts, kidneys, and the like. And on the same vein of your antioxidants, right, I'm looking at reactive oxygen species scavengers and how to try and enhance the time that organs can be preserved so they can travel further, like across the country or across the world to people who need them, as well as try and improve their uptake after transplantation by reducing the reactive oxygen species that are produced as a reperfusion injury following transplantation, which is a leading cause of acute rejection. So I'm really focused on trying to get something to patients. That's my ultimate goal.
That sounds incredible. And I know a lot of that work takes so much time through experimentation and getting through all the red tape and actually getting into clinic, getting it tested and actually getting to a point where it can be widespread. It does take time, but I have faith that through all that work that you're doing, you're going to be saving some lives, saving some limbs and saving some lives one day soon. What are some of the biggest challenges that you're facing with all of that?
In some aspects, it is the technology itself. So from, for prosthetic control, it's trying to find the right interfaces, the right surgical approaches. Then from limb transplantation, I'm currently at the point where I'm dealing with the FDA to some degree to try and work towards getting all of the preclinical data towards clinical trial in the next few years, which would be, that would be human patients looking at the side effects and then phase 1 or phase 2 clinical trials there. Most of the challenges are just time, really. It's time, the experiments are time consuming, the data analysis is time consuming. You're working with biology, which does not necessarily follow any sets of rules that you would like it to, at least not consistently. So you're constantly having to change your schedules and change times to be able to get things done. Other than that, it's just the capacity to generate enough data that is affirmative of what you're trying to do and make sure that you meet all of the regulatory steps along the way to get it into a phase 1 clinical trial.
Full on. Yeah, I can imagine that would be super tricky. Who inspires you? Is there anyone specific that inspires you to do the work that you do?
Inspiration's interesting. I mean, it kind of comes and goes. Sometimes you have inspiring conversations. Sometimes you read something inspiring. Sometimes I watch something inspiring that makes me ask why. But I think really, for me, it's just kind of preservation of life, So personal experiences, for instance, my son was born massively premature, 3 months early, and it was an enormous team that allowed him to survive on him as well a little bit, for being a survivor. But that takes full teams. It includes everybody from, nurses, doctors, specialists, engineers that create the devices that make sure that the babies are all the right temperature and that sort of stuff. And then my dad had a genetic heart condition that just popped up out of nowhere, had a pacemaker, had a transplant, both relatively around the same time. So for me, I see the wonderful things that we can do as a result of science, but also through those experiences, I see some of the limitations and some of the areas that we could improve. And, whether it's a premature birth or a transplant or any kind of medical situation that people experience through their lives, it doesn't just affect the individual, it affects their family and it affects the community as a whole, right? So there are people that will have to look after you while you have a broken leg and can't walk. For that time, you might not be at work, and so somebody else has to put in for you. Otherwise, maybe you're losing money because you're not at work. Maybe it means you're in a place that you don't get health insurance or all those sorts of things. So it's a complex system, and I think ultimately it's a community. And so by helping an individual, you're helping a community and really just contributing to the kind of world that I would like to live in, really. But I think really you can take your inspiration from anywhere. I find that conversations at scientific meetings or just conversations with people in general are what really inspires me. From this conversation today, for instance, there are things that pop up where I start to wonder about something I haven't thought of for a while. Like what am I doing with transplantation in general as opposed to just limb transplantation? Do I need to start focusing on those areas more broadly, or do I need to start focusing on them more generally?
Yeah. Sometimes it's good to take a step back and reflect on these things.
I mean, I think you do a lot of reflection in conversations where you just talk to people, really, right? You're having a conversation and telling somebody who you are while finding out who they are, what's important to them, expressing what's important to you, and hopefully finding common ground or common interest. So inspiration really comes on a daily basis.
Incredible. I love that answer. And for people who want to learn more about what you do, I don't know if you have any book recommendations or movie recommendations or even people to follow online.
Certainly follow The Traveling Scientist. It's my number one tip. I always enjoy a good sci-fi movie, just as a way of switching off from reality and thinking about how things could be without having to overthink how things could be.
Yeah, science fiction can inspire science, as we've shown here.
Absolutely. It's only science fiction until it's reality, right? Most of the reading I do is purely academic. I just try to read as much literature as possible, and then to switch off from that, I try to watch as much sci-fi as possible.
Cool. I love that balance as well. Science literature balanced with science fiction. Sounds nice. Aaron, I've got a couple of listener questions for you, if you've got a moment to answer those.
Let's do it.
But before that, each week here on Travelling Science, we make a donation to a charity of the guest choosing. And this week, Aaron has chosen to make a donation to Surf Life Saving Australia, which works to save the lives of everyday beachgoers around the country. And on average, they rescue 30 people from drowning every single day. So a donation has been made to Surf Life Saving Australia on behalf of Dr. Dingle. And if you'd like to make a donation to them as well, that would be incredible. And you can find the link in the show notes just down below. But for now, back to Travelling Science.
First one is from Constababble, and they were wondering how often you tell people that you're a tissue engineer and they ask you a question about Kleenex design. Does that ever happen?
Yeah. Throughout my PhD, if that question came up, I used to tell them that it was my idea to put the puppy dogs on the toilet roll.
Genius. That's sold. Even like a couple of days ago, someone was like, oh, look, there's the Kleenex dog. I don't know what the breed is, but you know the one. And I was like, I do know the one.
It's a Shar-Pei.
There you go. This guy knows.
Yeah, it's my idea.
Lovely. Another question from Marcia RD was wondering what types of tissue are your bread and butter, like easy to regenerate, versus what is something very challenging to work on?
Oh, good question. So the real successes in tissue engineering have been in skin and cartilage, because those are two avascular tissues. They don't need a good blood supply. Skin can get a lot of its oxygen through diffusion, and collagen is more of a supportive structure or an extracellular structure.
Very cool. And is there something really difficult that you just can't do or struggle to do?
I mean, I think to a large degree we can work with the majority of tissues, but when I think about something as complex as a limb, which is made up of multiple tissues, if you want to grow a piece of skin in a nice sheet that can then just be placed over a wound, or replace a piece of damaged skin or a lack of skin, that's a little bit easier than it is to take a flat sheet and place it around a hand and be able to form the fingers and things like that, because the tissues aren't that flexible. They're very delicate and brittle. So how do you make complex shapes like ears and fingers, or even eyelids, for instance, right, that are skin covered, very delicate, but also have lots of undulations in their topography that you can't just sit there and craft like you could craft it out of clay. So can we 3D print structures and grow skin on the external surface of those structures? Can we just grow skin that's in the shape of a hand that goes on like a glove and gets sutured down or glued down? So it's thinking about how to apply those to kind of complex geometries.
Yeah, really complicated. Yeah, I would never even think of something like recreating an ear or an eyelid. Yeah, it sounds a lot more delicate and complicated than you might initially think. Awesome. Thank you for answering those couple of listener questions. And just to finish off, I've got a lightning round, if you're ready for that.
Go for it.
All right, here we go. You're from Australia, but now you're living in America. Which country do you prefer?
Can't make that comparison.
Fair enough. If you could do something completely different with your life, what do you think you might have done?
I still don't know what I'm doing in my life. So, I'm just making it up as I go.
Rad. What do you love most about your job?
The diversity of people, the diversity of projects, and the general energy and enthusiasm behind a really good idea and making it reality.
Yeah, it sounds like you guys are working on so many incredible things. What do you hate most about your job?
Some of the administrative stuff can be tough. You spend a lot of time in bureaucratic red tape.
Yeah, I can imagine.
But it's there for good reason, or at least that's what I tell myself.
If you had $1 million budget, theoretically, what sort of experiments do you think are most important? What would you be working on next?
I would love to expand to have to be able to be running at a greater capacity than what I'm currently running at. So currently I have too many experiments on the table and not enough time. So if I had $1 million, I would focus on obtaining the preclinical data for clinical trials of organ and limb transplantation drugs.
Awesome. And last question, do you have a favorite tissue or a favorite surgery or a favorite limb, a favorite thing to work on?
You're asking if I'm a leg man? I'm trying to replace them.
Do you like hands or feet? Peg legs, hooks?
I like working with the limb transplant space. It's highly complex, but it is very tangible. You can kind of see the results immediately. You can immediately understand the importance of it. Whereas when you see somebody or something that's just had a kidney transplant, you don't necessarily know what's happened, and you don't necessarily know what the importance of that is. But when you see a limb transplantation, you can kind of really, or a advanced robotic prostheses, you can really understand the purpose. You can really understand the importance, and I think it's easy to kind of get people to be able to appreciate that and support that.
Fantastic. Thank you so much, Dr. Aaron Dingle, for coming on the show today and speaking with us all about prosthetic limbs and tissue regeneration and everything you're doing in the field of academia and medicine. It all sounds incredible, and I have no doubt that you are going to be, I'll say it again, saving limbs and saving lives, which you're probably already doing, but more so in the future. So thank you so much for everything you do. And just to finish off, considering everything we've discussed here, I wonder if you have one final piece of advice that you'd like to share with the listeners, maybe something they could take away and act on to improve their lives in some way. Do you have one final bit of advice?
Diversity drives innovation. Speak to people as broadly as you possibly can. Don't risk missing opportunities. You can learn amazing things from people that you wouldn't otherwise decide to talk to based on your own internal biases. So just get out there and have cool conversations with cool people.
So there you have it, legends. That was Dr. Aaron Dingle, tissue engineer, prosthetic practitioner, scientist, and science fiction connoisseur. I love this man, and I'm so proud to call him my friend, and I'm so glad that I got to share his story with you today, because I just feel like Aaron is so relatable. He's just a guy who loves science fiction, but then by watching something like Star Wars, decides that he wants to bring this seemingly futuristic technology to life by focusing his research on neuroprostheses and making robotic limb transplantation possible. It's just like Aaron said, it's only science fiction until it's reality. And another concept that Aaron highlighted was the importance of diversity and conversations. Speaking with a broad variety of people can be eye-opening, and you can really learn so much about the world and share a lot from your own world. And by having plenty of conversations with various different people, you can generate so many thoughts and ideas which could ultimately inspire you to do something incredible and change the world. So, as Aaron said, just get out there and have cool conversations with cool people. And that is exactly what we try to do here on Traveling Science. Have cool conversations with doctors, researchers, and experts from across the globe to share important information that can help us to live smarter, happier, and healthier. So thank you so much for listening in today. And to find out more about Dr. Dingle's work, you can check out the University of Wisconsin's Department of Surgery webpage, and that link is in the show notes just down below. And if you're wondering why I haven't posted anything for a few weeks, I apologize for that. I got quite sick and then I broke my ankle. So I've been spending a lot of time in rest and recovery mode, but I am endeavoring to get back into regularly creating science-based content for all of you. But yes, thank you for being patient in my absence. And if you appreciate this podcast, you can support us by checking out The Traveling Scientist on Patreon, or you could just leave us a 5-star review on Apple Podcasts or Spotify. That would be super helpful. Finally, if you stick around to the end of the podcast, I always like to leave you with a little secret. And this week's secret is that, as I mentioned, Aaron and I are good mates, and One thing we didn't talk about too much during this episode is food, but Aaron is passionate about food. And back in the day in Melbourne, when he was doing his PhD and I was doing my undergraduate, we decided one day that it would be a good idea to make fast food sushi. So we drove around to McDonald's and we got some Happy Meals and some French fries. And then we went to KFC and we got some Zinger burgers and some popcorn chicken. And then we went to Hungry Jack's and got some onion rings and Whopper burgers. Then we made a lattice of intertwined bacon and baked it in the oven, creating a sheet of meat. Then proceeded to dice up the fast food, wrap it up in that bacon, and create fast food sushi. And this is a meal that I'll never forget and something that I would never dare to recreate. I mean, it was possibly the greasiest thing you could ever eat. I didn't realize that the meat sweats was actually a thing, but it definitely is. So anyway, that is an epic memory that I share with Dr. Aaron Dingle from back in the day. And look at us now. Inspiring stuff. Anyway, thank you so much for listening, legends. Have a lovely week, and I'll catch you all next Science Sunday. Cheers.